Welcome to another exciting deep dive into AI research. Today, we're exploring DeepSeek-OCR 2, a groundbreaking model that's changing how machines read and understand documents. What makes this model special is something called Visual Causal Flow. Instead of reading images the way traditional systems do, DeepSeek-OCR 2 dynamically reorders visual tokens based on the actual meaning of the content. Think of it like the difference between a robot scanning a page line by line versus a human who naturally jumps to the most important parts first. The results speak for themselves. DeepSeek-OCR 2 achieves over 91% accuracy on the OmniDocBench benchmark, which is a 3.73% improvement over the original model. And here's the kicker. It does this while using the same computational budget as competitors like Gemini 3 Pro. The architecture follows a clean pipeline. Images go through a vision tokenizer, then a language model encoder, and finally a decoder that outputs the text. We'll break down each of these components in detail throughout this video. Before we understand DeepSeek-OCR 2's innovation, we need to understand the problem it solves. Traditional vision language models use something called Raster-Scan order to process images. Imagine reading a book by going pixel by pixel, left to right, top to bottom, like an old printer. That might work for simple images, but documents are complex. They have multiple columns, tables, figures, and formulas all mixed together. When you flatten a two-column document into a single sequence using raster scan, you end up mixing content from both columns. The model sees words from column 1 interrupted by words from column 2. Tables get scrambled because cells that belong together are separated by unrelated content. This is called context fragmentation, and it's a fundamental limitation of how most vision encoders work today. The position encoding is fixed based on spatial coordinates, completely ignoring the semantic structure of the document. DeepSeek-OCR 2 was designed specifically to solve this problem. The key insight behind DeepSeek-OCR 2 comes from studying how humans actually read, and it's nothing like how machines currently process images. Human vision has two distinct regions. The fovea gives us sharp, high-resolution focus on a small area, while peripheral vision provides low-resolution context about the surrounding scene. When we read a document, our eyes don't scan left to right like a printer. Instead, we jump to areas of interest based on what we've already understood. The paper describes this as causality-driven flow. Each eye movement depends on what we saw before. If we're reading a table, we follow the logical structure of rows and columns. If we're tracing a spiral, our eyes follow the inherent geometry. The key is that the ordering is driven by semantics, not by fixed spatial coordinates. This is the fundamental principle behind DeepSeek-OCR 2. Visual tokens should be processed in an order that reflects their semantic relationships, not their physical positions on the page. This simple but powerful idea leads to significant performance improvements. Let's look at how DeepSeek-OCR 2 actually implements this idea. The architecture is called DeepEncoder V2, and it follows an end-to-end pipeline. First, images go through a vision tokenizer based on SAM, the Segment Anything model. This is an 80 million parameter component that compresses visual information efficiently. Then comes something unusual. Instead of using a traditional vision encoder like CLIP, they use a language model, specifically Qwen2 with 500 million parameters. Why use a language model for vision? Because language models are built for causal sequential reasoning. By replacing CLIP with an LM-style encoder, they can apply causal attention to visual tokens. This is what enables the semantic reordering we talked about. The final component is DeepSeek's 3 billion parameter decoder with mixture of experts. Only 500 million parameters are active during inference, making it surprisingly efficient. The entire pipeline is designed to process documents the way humans do, with semantic understanding driving the ordering of information.
The Vision Tokenizer is a critical component that determines how much information can be packed into a limited token budget. DeepSeek-OCR 2 achieves remarkable compression. For each image crop, the tokenizer takes 896 patches and compresses them down to just 144 tokens. That's roughly a 6x compression ratio, achieved through window attention with minimal parameters. The clever part is the multi-crop strategy. The model processes a global view at 1024 by 1024 resolution, producing 256 tokens. Then it adds up to 6 local crops at 768 by 768, each producing 144 tokens. The total maximum is 1120 tokens. Why does this number matter? Gemini 3 Pro, one of the top competitors, uses 1156 visual tokens. DeepSeek-OCR 2 achieves better results with a nearly identical token budget. The tokenizer's efficiency is what makes this possible, doing more with less through smart compression.
Now we get to the heart of DeepSeek-OCR 2's innovation, Causal Flow Queries. This is a dual-stream attention mechanism that combines the best of both worlds. The first stream handles visual tokens using bidirectional attention, just like a vision transformer. Every visual token can see every other visual token, giving the model a global understanding of the entire image. The second stream introduces learnable causal queries. These queries are appended after the visual tokens and use unidirectional attention. Each query can see all the visual tokens plus any previous queries, but not future queries. Sound familiar? This is exactly how language models work. The magic happens when these two streams combine. Visual tokens maintain their global receptive field for pattern recognition, while causal queries progressively reorder the information for sequential output. Only the causal query outputs are passed to the decoder. This creates a natural bridge between visual understanding and sequential text generation, enabling semantic reordering without losing visual context. The attention mask design is where the dual-stream architecture comes together. It's a hybrid that combines vision transformer patterns with language model causality. In a standard vision transformer, attention is fully bidirectional. Every token can attend to every other token. In a language model, attention is causal, forming a lower triangular matrix, where each token only sees what came before. DeepSeek-OCR 2 creates a hybrid mask. The top left region is fully bidirectional for visual tokens, maintaining the ViT-style global receptive field. The bottom left region allows causal queries to attend to all visual tokens. The bottom right region uses a triangular causal mask for query-to-query attention. The formula looks complex, but the intuition is simple. Visual tokens get pattern recognition through bidirectional attention. Causal queries get sequential reasoning through unidirectional attention, and the cross-attention between them bridges both capabilities. This elegant design achieves the best of both worlds in a single forward pass. Training DeepSeek-OCR 2 follows a carefully designed three-stage pipeline that balances efficiency with capability. Stage 1 focuses on encoder pre-training. The Vision Tokenizer and LM-style encoder learn to extract and compress visual features. This uses 160 A100 GPUs across 20 nodes, processing about 100 million image-text pairs at high resolution. Stage 2 is query enhancement. Here, the tokenizer is frozen, and training focuses on the connection between the LM encoder and the decoder. The DeepSeek 3 billion parameter model is integrated with 4-stage pipeline parallelism. This stage teaches the causal queries to effectively bridge visual understanding and text generation. Stage 3 is decoder specialization. The entire DeepEncoder V2 is frozen, and only the language model decoder is fine-tuned. This doubles training speed, since gradients don't flow through the encoder. After about 20,000 iterations total, the model achieves state-of-the-art results with the same computational cost as the original DeepSeek-OCR. Let's look at the numbers. On OmniDocBench version 1.5, DeepSeek-OCR2 achieves 91.09% overall accuracy. That's the highest score among all tested models. Compare this to Gemini Pro 3 at 90.67% and GPT-4o at just 75%. The original DeepSeek-OCR scored 87.36%, so version 2 represents a significant 3.73% improvement. But raw accuracy isn't the only metric that matters. Edit distance measures character-level errors, and DeepSeek-OCR2 achieves 0.10, better than Gemini 3's 0.115. More importantly, reading order error dropped from 0.085 to 0.057, a 33% reduction. Remember, this model handles complex documents with tables, formulas, and multi-column layouts. The causal flow mechanism specifically helps with reading order by processing content semantically rather than spatially. These benchmark improvements translate directly to better real-world performance on complex documents. Let's dive into the code for running DeepSeek-OCR2 using HuggingFace Transformers. This is the official implementation from DeepSeek. First, you need the right dependencies. The model was tested on Python 3.12.9 with CUDA 11.8. Install PyTorch 2.6, Transformers 4.46.3, and Tokenizers 0.20.3. You also need INOPS, Addict, and EasyDict. For optimal speed, install Flash Attention 2.7.3 with the No Build Isolation flag. The inference code is straightforward. Import AutoModel and AutoTokenizer from Transformers, set your GPU device, then load from DeepSeek.ai/DeepSeek-OCR-2. Make sure to set Trust Remote Code to true, since this uses custom model architecture. The key optimization is setting _ATTN_implementation to Flash Attention 2.2. After loading, convert to bfloat16 and move to GPU using eval, CUDA, and to bfloat16 chain. For prompts, use the grounding format for document to markdown with layout preservation, or use free OCR for simple text extraction. The infer method takes base size 1024 for global view, image size 768 for local crops, and crop mode true for multi-crop. Now let's look at running DeepSeek-OCR2 with Unsloth, which offers optimizations for training and inference. Start by installing the latest Unsloth with pip install upgrade Unsloth. If you already have it, force reinstall with no deps and no cache dir to get the freshest version along with Unsloth Zoo. The Unsloth approach uses FastVisionModel from the Unsloth package. First, download the model using Snapshot Download from HuggingFace Hub. This downloads the Unsloth/DeepSeek-OCR2 model to a local directory. Then load with FastVisionModel.from pretrained. The key parameters are load in 4-bit for memory reduction, AutoModel set to AutoModel, Trust Remote Code true, Unsloth Force Compile true, and use gradient checkpointing set to Unsloth for long context support. The inference call is similar to the HuggingFace version, but with image size at 640 instead of 768, and an additional test compress set to false. The real power of Unsloth comes from fine-tuning. You get 1.4 times faster training, 40% less VRAM, and 5 times longer context lengths with no accuracy loss. There's a free Colab notebook ready for fine-tuning on your own data. Here's a third option, using the standard Transformers API, but with Unsloth's optimized model weights. This gives you the best of both worlds. The setup is identical to the official HuggingFace code. Same dependencies, PyTorch 2.6, Transformers 4.46.3, Flash Attention 2.7.3. The only difference is one line. Instead of loading from DeepSeek AI/DeepSeek-OCR-2, you load from Unsloth/DeepSeek-OCR-2. Same auto model, same tokenizer, same API, different weights. Why would you do this? Unsloth maintains their uploads specifically to work with the latest Transformers versions. There's no accuracy change. It's the exact same model, just with better compatibility patches applied. This is particularly useful if you're having version conflicts with the official release, or if you want to do LoRa fine-tuning later. The Unsloth upload is already prepared for that workflow. Both approaches give you the full 91% accuracy on OmniDocBench. The only question is which fits better into your existing codebase and infrastructure requirements.
Where can you actually use DeepSeek-OCR2 in production? The applications are surprisingly broad. Document digitization is the obvious one. Scanned documents, PDFs, even photos of papers can be converted to searchable, editable text while preserving the original layout. This is crucial for enterprises with large document archives. Table extraction is particularly powerful. Financial reports, research papers, and spreadsheet images often contain complex tables that traditional OCR struggles with. The causal flow mechanism helps maintain the logical structure of rows and columns. Formula recognition converts mathematical equations to LaTeX, whether they're typeset or handwritten. Academic paper parsing handles the complex layouts of multi-column research documents with embedded figures and equations. For enterprise workflows, think invoice processing, contract analysis, and form digitization. And for search and retrieval, DeepSeek-OCR2 makes visual documents searchable for RAG pipelines and knowledge bases. The model is production-ready and already deployed at scale.
Let's wrap up what we've learned about DeepSeek-OCR2. The core innovation is Visual Causal Flow, which processes visual tokens based on semantic meaning rather than fixed spatial positions. This is implemented through a dual-stream attention mechanism that combines bidirectional vision understanding with causal query reordering. The architecture achieves 91% accuracy on OmniDocBench while using only 1120 visual tokens, comparable to Gemini Ultra Pro. The 3 billion parameter model has just 500 million active parameters during inference, making it efficient for production use. Looking ahead, future research directions include longer context windows for processing entire books, multi-page document understanding, and potentially extending these ideas to video. The fundamental insight that semantic ordering beats Raster-Scan will likely influence future vision language model designs. DeepSeek-OCR2 is available now on HuggingFace and Unsloth under an Apache 2.0 license. If you found this breakdown helpful, please like and subscribe for more AI research explanations. Thanks for watching.